Well, it's my pleasure to start us off and introduce Jingxuan Wei, who is going to be giving us, he's a postdoc here at UTIG, and he's going to be giving us a talk on acoustically mapping the ocean, the progress and prospects of seismic oceanography. And he has an interesting history. So he actually started off as an engineer, but an engineer in geophysics, right? So he had a bachelor's in engineering and geophysics from, how do you pronounce the university's name? Julia?
Jilin.
Jilin.
Yeah.
Jilin. Okay, great. And then a master's in engineering out of Cornell, where he worked with Larry Brown on the in-depth 4, I guess it was, before he went off and worked with Bobby Reese at Texas A&M and did his PhD there. Since being here at UTIG, he's actually working with everybody, basically. He's been on 5 cruises. He's done both projects associated with the Campeche Bank, with Chris Lowry on the Chicxulub Impact Crater with me, and then a whole slew of projects associated with funding from BOEM and GLO to work on the Texas coast. He's also served basically as our other TA/instructor for the field course now for 2 years. Yeah. Great. And because of him, we now have this wonderful Sparker system that we've been using for all kinds of great research because of his connections with A&M. So, you know, his experience is his main research excitement is seismic oceanography, but I will say that he has incredible depths of capability in lots of other areas you won't hear about today, a lot of things below the seafloor. But it's really exciting to see how you can take the geophysical methods and apply them to really different environments and physical principles to understand the Earth. So with that, Jingxuan.
Thank you. Thanks, John. Good morning, everyone. So today I will be talking about an emerging ocean observation technology called seismic oceanography. It was first discovered by marine geophysicist, Dr. Steve Holbrook in 2003. So exactly 20 years ago. So after 20 years, it's still trying to emerge. Yeah. So there are only like 6 or 7 people around the world still actively doing it, and I am one of them. Well, I'm actually proud to be one of them because I really enjoy doing it, and I think it has huge potential. So for now, most of the oceanographers still view this method just with curiosity without actually knowing what it can do or what it really means. So today, I hope after this talk that you would agree with me that this is an interesting technique and it has potential, and more participation are needed from both the geophysics side and the oceanography community. I will first introduce this method and then followed by two case study of my own research to kind of talk about its development and a brief touch on the future possibilities. Oh, okay. So first, some background. I want to first talk about how do we observe the physical ocean, and then talk about what is seismic oceanography. And first, I will just briefly go through several ocean observation platforms. The first one is, of course, CTD, which is pretty well known. It's usually deployed on research cruises. It can collect full depth hydrographic information and also collect water samples. And the second one is mooring. It comprises of a float at the surface and anchor at the water bottom. So there's sensor that can be installed along this cable, usually at the fixed depths to measure temperature, salinity, or current speed. But there's also some other moorings that are more advanced that have the sensor that can move up and down to monitor the entire water column. So both the CTD and mooring collect data at a fixed location. And the third one is a drifter, that it follows the current and collects sea surface properties. And here is the global Argo network. This instrument has some autonomous capability, so it can dive and drift with the current, and while it ascends to the surface, it will collect temperature and salinity. So on average, the maximum depth it can reach is about 1,500 meters. The last figure shows the example of Argo trajectory. The yellow dots means when it was at the surface. So there are also the underwater glider which is currently the most popular platform for physical oceanography because it has great autonomous capability, and it can be equipped with a variety of sensors, and it is pre-programmed to travel in the ocean as a sawtooth pattern. It can reach a depth of roughly 1,000 meters, and it can operate remotely, sometimes even during a hurricane. However, its lateral resolution is limited by the slow speed. It travels at about 0.3 meter per second. And of course, we have the satellite that surveys the surface of the ocean. Here's the example of the SWOT satellite that was launched last year. It is currently, I think, the highest resolution satellite that provide the ocean measurements. So all of these comprises a regional ocean observing network. However, these platforms have limitations. They don't provide enough resolution in the horizontal direction. So they usually provide time series at a single location, such as moorings, or acquire measurements in a single direction or travel paths, like drifters or gliders, Argos, or just surface only surveyed only the surface of the ocean. However, as we know, ocean processes happens on a variety of scales, as shown in this figure over here. The ocean processes, it can range from scales of seconds to thousands of years, and also from centimeters to thousands of kilometers. So variability in the scale of in the process at one scale can affect variability at process at other scales, right? So it is important to monitor and study the ocean across all these scales. However, we have a considerable observational gap, which is around the mesoscale and submesoscale that have relatively short time and spatial scales. And as shown in this red box over here, so eddies and fronts and internal waves are within this range. And through these processes that the majority of ocean energy is mixed and transported. So the lack of observation of these processes contribute to large spread in our climate models. Therefore, we need a technique that can fill in this gap. And that's where seismic oceanography comes into play. So this method is actually an adaptive version of reflection seismology. As we know, reflection seismology is really used to image the solid Earth. It turns out we can also image the temperature and image the water column because of temperature and salinity differences that cause impedance contrast that can be resolved by the acoustic source, which is usually air gun. So here's the demonstration of the system. A ship tows an acoustic source that emits signals into the ocean. When it meets a reflector, it's reflected back and received by a linear array of hydrophones. And along this reflector, so each point is measured multiple times, and the eventual stacking of signals at these points produce a vertical slice or 2D snapshot of the ocean, as shown in the figure down here. So the advantages of seismic oceanographies are, firstly, it provides a multi-dimensional observation at high resolution, usually on the order of 10 meters. And second, it has great spatial coverage. It can penetrate to abyssal depths, also spans horizontally for hundreds of kilometers. So because of its high resolution and great coverage, it is suitable to observe and study the mesoscale and submesoscale processes. So unlike the interfaces, the sharp interfaces in the solid Earth, physical properties in the ocean change gradually. So what the seismic is really imaging is the gradients of ocean properties that represent the little changes between water masses. So as shown in this figure, these are the vertical gradients of water properties. We can see changes in temperature and salinity causes changes in reflectivity. And on average, the contribution to reflectivity for temperature is about 80%, and salinity is about 20%. So this last column is a synthetic seismogram produced by the convolution of source wavelength with the reflectivity. And we can see that this seismogram, it doesn't capture all the detailed information of salinity and temperature. So, and also because temperature has a dominant effect, the seismic image is essentially an image of the temperature gradient that is smoothed by the wavelength of the source. As shown in the last two panels, it is a coincident measurement of temperature and seismic. We can see the changes in temperature matches the seismic response. And this is a more straightforward comparison between conventional method and seismic oceanography. The one on the left is an eddy captured by CDD. It has a horizontal resolution of 1.5 kilometers. And on the right is an eddy captured by seismic. It has resolution of 12.5 meters. So it is pretty cool to see the image of the ocean, but what can we do about it, right? How can we analyze the data? So of course, we can invert for temperature and salinity. So this is a very cool result of full waveform inversion of temperature and salinity of the Mediterranean outflow. This data was collected by the European Geophysical Oceanography project, which was the last dedicated cruise for seismic oceanography. And it was, oh yeah, I should mention this. The triangles on the top are coincident expandable CDDs collected during the seismic cruise. And it was after this cruise that people realized it is actually impossible to accurately invert temperature and salinity without coincident hydrographic data, because the acoustic source of seismic acoustic source is always band limited. So low frequencies, for example, below 5 Hertz is always missing in the seismic data. And these two images are produced by extracting low frequency information from these coincident CDDs. And this is one of the challenge that preventing seismic oceanography from being popular. So if consider this, if we, a cruise that collects seismic data and also coincident hydrographic data could be very expensive. And for ocean observations, we probably want to do repeat surveys, right, to capture the temperature changes, and that would be even more expensive. Yeah, but there might be a solution to this problem. I will talk about it briefly later. And we also can quantify dipycnal diffusivities. We can also call it turbulent mixing rate. So dipycnal mixing, it refers to mixing of fluids across isopycnals, which are equal density surfaces. So basically, it means the mixing of fluids with different densities. And it is usually caused by breaking of internal waves, and it is crucial in maintaining the global overturning circulation. And this method is based on the assumption that seismic reflections follow isopycnals, and which is usually true because temperature usually dominates the density variation. So this is an example of the spatial distribution of mixing along the continental slope. So this kind of knowledge on the patchiness of mixing is very important to build accurate climate models. And to extract turbulent mixing from seismic data, we use this isopycnal slope spectra. So this method is developed from towed instrument. For example, this towfish called marlin, it was towed along isopycnals and measured 2 parameters. One is mixing rates, the other is the displacement of the isopycnal. And the mixing rates and the displacement can be related through this spectral analysis. In this figure, the horizontal axis is wave number and vertical axis represent energy. So we can see there are 2 distinct subranges. The lower wave number that has a negative slope corresponds to the internal wave subrange, and higher wave number that has a positive slope corresponds to the turbulent subrange. And these 2 subranges are described by these 2 equations. So what does it mean? So it means if we know the displacement of isopycnals, we can estimate mixing rates from this relationship. And seismic images exactly captures the displacement of isopycnals. Therefore, we have the reflection slope spectrum. And on the left shows the tracked reflections that represent isopycnals. And on the right shows the spectral analysis of these reflections. So it also shows two distinct subranges, internal wave and turbulence. So by fitting this turbulence subrange to this equation, we can estimate the turbulent mixing rates. So this method is pretty well developed, but it still has a question. A problem is that there still needs a consistent and standardized way to analyze data so that uncertainties, especially from seismic data processing, can be quantified. And then, so I will present a case study with this slope spectral method to show you the capability of seismic oceanography in analyzing mesoscale processes. Why is mixing important? Because it maintains the global overturning circulation by bringing denser water up to the surface. So without mixing, the ocean will be a stagnant pond of water. And it is well accepted that average diffusivity mixing on the order of 10 to -4 is required to maintain the current global overturning of circulation. However, observations suggest above 1,000 meters, so in the main thermocline, the diffusivity is only on the order of 10 to -5, which means there's a substantial amount of mixing budget is missing, right? And we do have evidence that enhanced diffusivities above the background value are found above rough topography and also under storm tracks. So which means the external energy source into mixing is from winds and tides. And here's how winds and tides contribute to turbulent mixing. Figure on the left, we can see the internal wave is generated by wind at the sea surface or by tidal currents at the seabed. So as the internal wave propagate, it loses energy and eventually break, result in energy dissipation in smaller scales, which is turbulent mixing. And tidal currents flow over topography, generate internal tides that emanates away from topography as tidal beams. But wind, usually as a storm, is an impulse forcing that acts on the ocean surface that can generate a kind of internal wave with frequency close to the inertial frequency, which is the Coriolis frequency. And we call this kind of internal wave near inertial waves. And this kind of internal wave can propagate downward through interaction with anticyclonic eddies. And I use these data to conduct my research. This was one of my PhD chapter. And I used the seismic data collected by the CREST experiment in 2016 from January to February. So the white lines shows the seismic location is from the east of Rio Grande Rise to the Mid-Ocean Ridge. The total length is about 1,600 kilometers and separated as different segments named line 1A to line 1F. And I also used the co-located CTDs that was collected by this GO-SHAPE program in 2003 and 2011. The spacing between the CTDs is about 50 kilometers. And I use these CTDs to aid the interpretation of seismic data. Oops, sorry. And I first created synthetic seismograms from those CTDs and found that from these two times, the reflectivity shares similar characteristics. Firstly, we observe a band of high reflectivity between roughly 400 and 800 meters. And most interestingly is this isolated pike of high reflectivity surrounded by low reflectivity at from 23 degree to 26 degree west around the depth of 1,200 meters. And we can see it over here too. And this is also observed in seismic. Okay, you'll see it later. Oh yeah, it's here. So this is the thermal helium fine structure imaged by seismic for 1,600 kilometers. Okay, from west to east, and this is line 1A, this is line 1F. And we see a band of high reflectivity between 400 and 800 meters, which is consistent with the CDD synthetic sections. And reflection characteristics varies from stronger continuous to weaker discontinuous, which means so stronger reflections, it represents higher temperature gradient, so which means stronger stratification. So weaker reflections means weaker stratification. And we see this black box over here that's above the mid-ocean ridge. So we see the reflection is super weak and clearly disrupted, implying the mid-ocean ridge is disturbing the upper water column. And we also see this blue box showing this kind of boundary structure is the same of the isolated pack of reflectivity we show in the we see in the synthetic section, and we see the location of them. They match pretty well, and also the depths. So what are they? I don't know, and I think no one knows, because this is the first observation of this kind of structure, and they look like some kind of boundaries between water masses that is stable and lasts for a long time. But without coincident hydrographic data, we cannot determine what they really are. So here is the corresponding high resolution diffusivity maps derived from the seismic data. I'm only showing data above 1,000 meters because below 1,000 meters, there are few reflections can be tracked, so they cannot be used to derive mixing rates. And the first observation we see is that the turbine mixing in the thermocline is heterogeneous, with a lot of places exceeding the background value of 10 to -5 meters squared per second. And the highest diffusivity is above mid-ocean ridge. And we also see over here, another pack of high mixing rates that penetrates above 1,000 meters, right? So because this place is away from rough topography, so we think that this probably caused by winds. And then we calculate the wind stress for 60 days prior to the seismic survey. And as shown in the first figure, the horizontal axis is time, vertical axis is wind stress. And we did observe a storm 30 days before the seismic acquisition. So here is the storm, and here is the seismic acquisition. And we also plotted the simulation of wind stress during the storm and at the beginning of the seismic survey. And we can see that this storm has substantial increase in strength in the near initial frequency range, which means it is capable of exciting near initial waves. And because we see this, the entire region is under the influence of the storm. And this actually raises another question. We go back to this high resolution diffusivity map. We see that the deep penetration of enhanced mixing is over here, right? It's not across all this region, but this location is affected by high wind stress. So what is causing this depth difference? Because sea surface mesoscale flow strongly affect how near initial wave propagate. So we look into the sea surface currents. And surprisingly, we did observe an anticyclonic eddy during the storm. So, and the eastern edge of this eddy is located exactly where the the deep penetration of mixing happens. So we propose that this anticyclonic eddy provide pathways for deep propagation of near inertial energy. We can actually further explore how deep this energy propagate. And this is the seismic image of line 1B and 1C, and also their corresponding diffusivity maps. We can see this mysterious boundary structure, right, in line 1B and 1C. because we believe they are some kind of long-term processes, they might share similar thermohaline properties. However, clearly we can see that the boundary in line 1b is dipping to the east, along with the reflections above it, while the boundary in line 1c remains horizontal, as well as the reflections above it. So this means this part is undergoing shear instability. And the diffusivity of this boundary is higher than this one. So this one has diffusivities close to the background value. So this means this kind of difference can be attributed to the deep propagation of near inertial energy. So the conclusion would be the presence of this eddy drains energy downwards to almost 1,300 meters at this location. And the downward propagation speed for this near inertial energy is about 47 meters per day. And this observation can be compared with other hydrographic observations and simulations. The left two figures shows the deep propagation of near inertial energy down to 800 meters and 500 meters, observed by moorings. The horizontal axis is time and vertical axis is depth. So this kind of process or phenomenon is called inertial chimney effect. So this is a simulation. We see the rapid deep propagation of near inertial energy at the influence of anticyclonic eddies. So without the eddies, it only penetrates to about 700 meters. So some key points from this study. Firstly, mixing is heterogeneous in the South Atlantic thermocline, modified by the presence of storm and rough topography. And the Middleton Ridge enhances diffusivity across the entire water column by at least 1 order of magnitude. Enhanced mixing away from topography is most likely caused by a storm. And an anticyclonic eddy provides pathways for the deep propagation of near inertial energy down to at least 1,300 meters. And lastly, this propagation speed is about 47 meters per day. So as you can see, the seismic method can provide a really detailed spatial distribution of mixing that can aid our interpretation of mesoscale processes. However, this method is not popular. It's still not popular because of two reasons. And first, as I said before, is lacking a standard way to analyze the data. And second, the derived mixing have not been properly compared with macrostructure measurement, which is a direct measurement of turbulence. So in the third section, I'm going to present a workflow that I developed that I hope can be served as a standardized workflow to derive mixing from derive mixing from seismic data. It will get a little bit technical from here. So noise. For water column seismic data processing, noise is the biggest challenge because the reflections in the water column is about 1,000 times weaker than the subsurface. However, how does noise affect the slope spectral shape has long been overlooked. People usually just apply a bandpass filter to preserve the central frequency range for better signal to noise ratio. But based on my experience, that is not enough. As shown in this figure, the first row is the a piece of filtered seismic data, and it is spectrally analyzed. And here we see three subranges: internal wave, a supranarrow turbulent subrange, and a noise subrange marked by this green line. This means the turbulent subrange is dominated by noise. And this will cause inaccurate fitting of the turbulent subrange, then inaccurate derivation of mixing rates. And so in this case, people usually just apply a Gaussian smoothing filter. As shown in the second row, we can see after the smoothing, there are more reflections can be tracked and the longer turbulent subrange can be recovered. However, this smoothing also caused this spectral roll-off because high wave numbers have been smoothed out. But the biggest problem of smoothing is that it changed the derived diffusivity. We can see there's a 0.4 difference in logarithmic units before and after smoothing. This means noise and smoothing introduce great uncertainties into this method. So to really understand the effect of noise and smoothing, we did a synthetic modeling. So we created this sound speed model that with displacement that simulates internal wave and turbulence. So in other words, these two equations are programmed into this sound speed model. And then we did a full wave field simulation across this model. And this figure shows an example of a simulated shot gather. And this one is a processed, noise-free seismic section that have equal levels of turbulence everywhere. Then we did a slope spectra on this synthetic data set. And the first row is the noise-free data set to just explore the effect of smoothing. And it turns out smoothing didn't really change the derived mixing rate. There's only a 0.03 difference in logarithmic unit. The only problem is it removed the sum of the high wave number, right? And the second row is the noise added data. We can see noise is preventing the tracking of reflections. It also increased the diffusivity value. And further smoothing of this noise added data results in a bigger increase in the derived diffusivity. So the conclusion for this test is the presence of noise led to overestimation of diffusivity, and the further smoothing of noisy data exacerbate this overestimation. So it's important to remove noise, right? Then I apply this machine learning technique. It's a supervised machine learning. However, it didn't work very well. It removes a lot of useful reflections. I think it is due to we don't have very good ground truth to construct the training set. So in the future, I think we should explore the unsupervised machine learning that doesn't require ground truth. So I went to a very traditional method of reflection seismology with its FK filter. It's represent frequency wave number filter. So it's a two-dimensional Fourier transform. The figure on the left is an noise-free synthetic shot gather and its corresponding FK spectrum. And the figures on the right shows the procedure of the denoising steps. So I'm not going to get into too much details about it. So basically, this cone shape is the filter, and outside this cone shape has been filtered out, so noise have been filtered out. The advantage of this method is that we have control over how many wave numbers we want to preserve. So it's a trade-off strategy between the signal to noise ratio and the wave number. For example, if we have a noisy data set, we will want to apply a narrow filter. So that means to remove more high wave numbers. If the data is less noisy, we can apply a wider filter, which means preserve more high wave numbers. Because this method, it modifies wave numbers, right? So we need to understand how does it affect the slope spectrum. And I apply this method to the synthetic noise-free data set, and also the crest seismic data that I mentioned in the last chapter, and also a high-resolution data collected by Chris and Jamie last year over the Campeche Bank. And I found that this roll-off wave number in the slope spectrum is related to the dominant frequency of the data. For example, in the synthetic test, the roll-off happened at wave number 0.03. And in the FK spectrum along the filter, this wave number corresponds to 39 Hertz, which is exactly the dominant frequency of the data. And it is true for the other real data sets as well. So this means we can quantitatively control how many wave numbers we want to preserve based on the dominant frequency and the noise level of the data. And this is a noise attenuation result. So this is the Campeche data set. It was a high resolution seismic survey. So a small shot spacing was used, which is good for subsurface imaging, but it creates very strong previous shot multiples in the water column. And this is actually the noisiest water column data set I've ever seen. But the denoising works pretty well. The top shows before the filter, the middle is after filter, and the last one is the difference between the two. We see there's no, the amplitude haven't been affected by this filter. And so by applying this method, I want to explore how accurate the derived mixing rates are. So I compare the seismic derived mixing with the direct measurement of turbulence. Here I'm showing two iconic studies of physical oceanography. The first one is the Brazil basin experiment. It was conducted in 1997. They collected vertical profile of mixing rates from middle ridge to the ocean interior. And this was the first time that people found evidence that rough topography enhanced mixing in the water column. And the reason that I compare this Brazil basin experiment with the CREST seismic data, because they were in a similar geological environment. They both extend from middle ridge to the ocean interior. And the second oceanography data that I use is the HOME experiment. It was designed to study the mixing around the Hawaii ridge. And it used the towed instrument Martin that I mentioned before. The red lines shows the trajectory of the towed instrument, and here shows the depth of the measurements. So I'm only using the cross ridge measurements because they align pretty well with the direction of the seismic data. And this seismic data was collected in 2018 to study the subsidence structure of the Hawaii Emperor chain, Hawaii Emperor Seamount chain. I was actually on that cruise, and that was my first research cruise. Yeah. So this is the cross ridge comparison. The blue line is the microstructure measurement by the towed instrument, and the green line is the seismic line 06. Yellow one is the seismic line 02. And we can see that the microstructure and seismic line 06, sorry, they match pretty well. They both measured high turbulence on the top of the ridge and the rapid decay of mixing away from the ridge. This actually makes sense because they are almost at the same location and the orientation of the survey is pretty similar. And the mixing rates measures by seismic line 2, however, well, it shows high mixing at the top of the ridge, but the decay of mixing is way slower. So I think this is caused by the additional topography on both sides of the ridge. And it is worth noticing that you see the seismic data didn't capture the extreme values of high turbulence. This actually makes sense because the method is based on tracked reflections. There are also, in seismic images, there are also weaker reflections that cannot be tracked. And there are other methods that can derive higher mixing from those weaker reflections, but that would be a completely different topic. This is the comparison from the mid-ocean ridge into the ocean interior in the main thermocline. The blue line is the microstructure and orange is the seismic. So I think this is a pretty comprehensive comparison because we see they exhibit a similar decaying pattern from the mid-ocean ridge, and the mixing level also matches pretty well. The bottom figure is a power law fitting between the distance away from the mid-ocean ridge and the decay of mixing. And we see the fitting between the two methods also match pretty well. So I think this not only verifies the seismic method, the accuracy of seismic method, but also has other scientific implications, because I think it's kind of a cross-validation that at two different locations, at two different times, from the mid-ocean ridge, it took about 1,000 kilometers for the mixing rate to decay to the background level. So this relationship could be, I think, it probably could be parameterized into climate models. And so I developed this standardized, well, I hope standardized workflow to derive mixing from seismic. It is not ideal because it's removed some of the high wave number, depends on the noise level of the data. So in the future, I think we should explore more advanced noise attenuation techniques. And some key points from this study. Firstly, noise affects reflection slope spectral shapes and led to overestimation of mixing rates. And we developed a processing workflow that adopt this kind of trade-off strategy. And third, the mixing rates, the derived mixing rate are in good agreement with direct measurements, suggesting this flow can be served as a standardized procedure. And four, starting from the mid-ocean ridge, topography is affecting turbulent mixing all the way up to thermocline and extends for 1,000 kilometers into the ocean basin, suggesting the topography is affecting mixing at very large scale. And the last one is this similar decaying pattern from mid-ocean ridge provides an opportunity to better the parameterization of turbulent mixing in climate models. And I will briefly talk about some future possibilities. I listed three goals of seismic oceanography in the future. So firstly, we have a short-term goal is to develop a consistent and reliable method to analyze the data so that uncertainties and errors can be quantified. And in particular, we need a standardized method to estimate temperature and salinity from seismic in the absence of coincident hydrographic data. And second, of course, we need better noise attenuation techniques. And the midterm goal is the numerical modeling of seismic imaging of time variant thermal heating structure. This would require a complicated coupling between numerical modeling of fluid dynamics in small scales and also full wave field seismic modeling. But this kind of modeling will be super helpful to test the accuracy of different methods, and also I think it will improve, provide more insights into how we improve the climate models. A long-term goal, of course, we hope to have a portable seismic acquisition system that is dedicated for seismic oceanography that can be deployed from smaller vessels along with other hydrographic instruments. And this is a proposal that I just finished writing with Shoshu. And this proposal is submitted to NOAA Ocean Exploration. So this program is seeking ocean technology to acquire fundamental ocean variables such as temperature, salinity, density, preferably full ocean depth. So I think this the goal of this program fits the capability of seismic oceanography pretty well. And we propose to use the CASI 21 seismic data along the Cascadian subduction zone. And the key thing about the key advantage of this project is there's a lot of oceanography sensors in this region. For example, these glider measurements, the moorings, they are coincident with the seismic. So it provides a valuable opportunity for us to quantify errors and also develop standardized workflows. And there's also this 2 kilometers high resolution ocean model at this region that we can compare to. So seismic can be served as a ground truth for this, that can be compared to this model. And hopefully we can better the parameterization of the model as well. And I should mention, so for this project, we will test a machine learning technique that hopefully can derive temperature and salinity in the absence of coincident hydrographic measurements, so that we hope to kind of broaden the application of that seismic oceanography. So after this short-term goal, we can unlock the potential of enormous legacy seismic data around the world. This is a map of legacy seismic data compiled by my colleagues. We can see there's the red and pink polygons are data collected by industries, and the water column data are useless to them, right? So I do think that some key solutions to some of our small scale parameterization lies in those models. Lies in those data. Yeah. And this will also be a great opportunity to build collaboration between research institute and the industry. And this is a future plan that probably work with Alexei and Patrick to use the data from around the Arctic region, because these data were collected using a portable seismic system, a mini GIGAN 300-meter streamer. It would be interesting to see the capability of this system in ocean observation. And it will also be interesting to see from the scientific perspective, how can we, what kind of information can we provide for the research in the Arctic region? Yeah, and that will be it. So before I end the talk, I want to make some acknowledgement to people in our institute who have supported me and contribute to this super small field. My three advisors, Sean, John, and Chris, thanks for supporting me in every aspect of my research. And also want to thank Shuo, Zeyu, and Benjamin for helping me with the NOAA proposal. And probably in the future, I will work with Alexei and Patrick for another proposal. And also supports from Damien and Jamie, and also our incredible staff members, Mark, Tom helped me with technical problems, and also Sarah, Jessica helped me with proposals. Thank you.
Okay, we have questions. Yeah, Chris.
Great talk, Jingxuan. That was really interesting. When you're talking about the mixing at the mid-ocean ridge and how that propagates for 1,000 kilometers, is that the mid-ocean ridge itself causing mixing that then works its way through the water column for 1,000 kilometers, or is that like roughness of the seafloor because you get all the abyssal hills?
Yeah, I think it's roughness of seafloor that across all the way into the basin. So I think I will work with John to calculate the roughness of the seafloor, from the mid-ocean ridge, and to correlate with the mixing we see in the upper ocean. The problem is because the seismic only image the upper ocean down to like 1,200 meters. So I don't know how well they will correlate, but it will be interesting to see the result.
Cool.
Yeah.
Do you get a similar mixing effect from like seamounts and like Walvis Ridge over there? I guess you don't have data across those things, but would you expect there to be?
Sorry, from where?
Just from like other large bathymetric features.
Oh, yes, of course. But the decay of mixing will be different. It depends on, actually there's a parameterization method based on the slope of the topography. So it's caused, because the mixing is caused by the tidal beam away from the topography, so it's related to the slopes, right. The slope of topography. Yeah. So for example, the Hawaii Ridge, it has a higher mixing, and also the strongest mixing probably is around the how to pronounce that, the deepest trench, the Marianas. Yeah, Marianas. Yeah, yeah, that's right. Yeah. Does that answer your question? Sorry.
Yeah, it does. That's
We
cool.
have one up here. You can throw the microphone to Harm. Nice.
Great talk. Yeah, Chris already answered my first question, but I'll start with a comment. When I was a grad student, there was a fellow grad student who was trying to explain why some ocean bottom seismometers that were deployed for some time were really noisy and others were not. And his basic conclusion was that if a storm would pass linearly over a certain study area, then the waves wouldn't propagate deep enough, and you more or less indicate the same thing. But if you had multiple storms or a storm change direction, you could maybe generate some standing waves that actually really propagate all the way down to the seafloor. It was an interesting conclusion. I don't know if it's true, but my question is, would it be possible that in the KC area or other places that you look at the ocean bottom seismometer data to see if, for example, when there's a storm passes, like what really the propagation effect of the seafloor is?
Well, that's a great question, but I've never done that before. But I think
I know you haven't done it, but I was wondering if
yeah.
But wondering if it would be helpful. I mean,
yeah, I think it will be very interesting to try. Yeah.
You have the data, presumably, right? I mean, in some places, both in the CREST data and the KC data.
Yeah. Yeah, that's right. Yeah, but how deep the storm generated energy propagate is still kind of a debate.
Yeah.
So we don't have from the physical oceanography point of view, we don't actually have sound evidence of how deep the near inertial wave propagates. So there's debate over like, it's only dissipate at the base of the mixed layer, or it propagate to like 1,000 meters, or it propagate to 3,000 meters. So I don't know the answer to that question, but I think it would be interesting to see.
I mean, it would only really be interesting to look into it if you understand the context. I mean, if you would actually know more or less what the weather was at a certain time in the past during the deployment, then it might be interesting ways to kind of see like how it came about. Just thought.
Yeah, thank you. Yeah, I think that's a great.
Good catch.
Yeah, just want to comment that we during the KC cruise we did have deploy ocean bottom seismometers in shallow water, and we did have several big storms. And I think that we have the data available to test what Harm was talking about. So like maybe that will be another project for you.
Okay, thank you. Yeah, that's a good idea.
Okay, yeah, Ed.
Hi, yeah, that was fascinating talk. Thanks.
Thank you.
So I guess you mentioned that one of the big drawbacks is that you have to go on a cruise, and cruises are expensive, and also they tell you only about a small part where you're going. So with that in mind, so I know also there's people putting acoustic sensors into Argo floats now. So do you think you could use those sorts of methods to look at the ocean? Because that's mainly looking at more deep earth seismology, but do you think you could use that sort of data to get like ocean measurements on a bigger scale than an Argo?
Yeah, sorry, I didn't understand clearly. Which kind of data you're
So
saying?
it's like the seismic signals, but just from one float drifting around.
Oh, okay.
So
okay.
like the same as the Argo data, but
Argo data. Okay.
but instead of being a direct measurement, they take the acoustic waves.
So they're putting hydrophones on Argo floats.
Yeah, there's a
to
group
measure low frequencies.
Oh, I don't know that. Yeah,
I didn't know that either.
yeah, it's like a group in Nice or something.
Huh.
But yeah, I didn't know if you could use that sort of data to get a better view of.
Wow, that's a very interesting insight. Thank you. I think I should look into that.
Okay.
Yeah. Yeah, I don't know. Sorry. Yeah,
that's great.
Yeah.
Benjamin.
Ooh.
Really incredible talk, Jingxuan. You talked about, the mixing caused by storms, and then also the mixing that's sort of driven by topography. It's remarkable to me that two different measurements taken like decades apart, you would see like the same basic structure of mixing. Yeah, I learned something very new today that blew my mind. I'm just wondering if you could help me bridge the gap between those timescales, and how does mixing vary on like an annual timescale, or sort of like a multi-annual El Nino, other kinds of natural fluctuations? How do those kind of changes in mixing compare with the orders of magnitude difference that you see across the global ocean?
Yeah, that's an excellent question. A mixing happens usually intermittent and not uniform, so that's why it's very hard to observe. And so I don't know how to, because I'm not an oceanographer. I'm trying to be a physical oceanographer. I'm still learning stuff.
I think you're doing a great job.
Thank you. Yeah, but to answer that question, so I can tell you what I know. So in terms of building climate model, I think for ocean models, for example, for now, the models is still like pretty, I would say, how to describe is pretty coarse. So for example, to parameterize the mixing above the topography, they will just use exponential decay or linear decay. So people really don't know what happens in the ocean interior. So there are extensive other measurements that have been conducting, and also the underwater glider have been equipped with the shear probe microstructure sensors. So I think that's from my limited understanding, that probably is a future question that needs to be answered. That how the intermittent mixing relate to the longer scale of ocean climate phenomena. And that's actually I remember I read this paper. That's the lack of mixing. The lack of observation of these small scales, that intermittent mesoscale like fronts that they will dissipate in several days. The lack of mixing of this kind of phenomenon is exactly the reason why we cannot forecast the climate more than a month, for a longer time scale. Yeah, that's one of the problems.
Thank you.
I got one sort of longer, now or even longer timescale question. So obviously, given the potential that seafloor topography changes our mixing rates, I'm curious if there's been attempts at looking at times of, say, higher tectonic rates, say the Cretaceous, and what that does to our ocean mixing. I mean, do we have a much better mixed ocean when the tectonic rates are higher, and that has a climate effect? Just throwing it out there.
Awesome question, but I don't know. I've never actually, I've never read any paper about that. I think that would be an awesome question to explore. Yeah. Well, thank you. I received a lot of feedback today that could be a future research direction. Yeah.
Great. Well, let's thank Jingxuan one more time. Oh, wait, there's a question there. Sorry, go ahead.
Yeah, I just had a quick question related to Benjamin's question. So you showed a map of the data availability toward the end. So I'm just wondering what the temporal coverage of the data and how far does the data go back? And is there enough to look into how the ocean mixing changes with global warming?
Yeah, I think so. Those data, I think that's a question we need to talk to the industries. Well, they definitely collect data over decades. Probably, I think maybe the high quality data, maybe at least I would say 20 years, right? And they have 3D data or sometimes even 4D data. But I don't know how could they resolve the the long scale problem. But for example, the 3D data that was collected over several days can clearly image the submesoscale features, that has been evolving during the seismic acquisition. And I have colleagues that actually doing this research that for 3D seismic volume, this line, for example, is collected in day one, and then the cross line is collected in another day, and we can actually see how the current is moving. So that kind of parameterization, I think, is more, well, from our perspective, is probably more easier to understand, compared to a much longer scale. But of course, I think if we look at the data across decades and derive some average, parameters that maybe aid the understanding of a long-term phenomenon. Yeah.
And we're in an interesting time because a lot of the first really good 3D surveys are just being publicly released. So some of these things, this is sort of, we're starting to see every single year, the Gulf of Mexico gets more and more 3D surveys just suddenly pop up as publicly available because they have to release them after 25 years. So, yeah.
I was wondering on that, is it also possible that, for example, energy companies are more willing to give you the data not to the seafloor, if you don't look at the subsurface?
Yeah.
Does it mean that the data are easy? I'm sorry, yeah. So I was thinking that because you're looking at the water column, you think that maybe you're not really a competitor for the energy companies, and maybe more data is available.
Yeah, that's a good question. That actually depends on if you have the right people to talk to.
Yeah.
So yeah, for example, I have a college in UK that they have a connection with industry that with BP and Schlumberger, they have access to several pretty good quality seismic data, 3D seismic data. And my previous advisor, Bobby, he tried to reach to guy in Shell that he did his internship there, but they are not open to the access to data. But so I think that depends on how we build the collaboration.
Thank you.
All right, now why don't we thank Jingxuan one more time? And there's going to be a lunch forum that Chris Lowry is leading. So meet in the lobby in 15 or?
All are welcome, students, non-students, people who are hungry.
Right. Okay, hungry souls to the lobby in 15 minutes.
Thank you, Harm. Yeah, thank you.